Surds. We start off with rational and irrational numbers. Consider the following numbers: 1 over 3, 0.92, 4 over 9, 2 over 5, and 0.4. Each of the above can be expressed as a fraction, that is a third, 92 over 100, 4 over 9, 2 over 5, and 4 over 10. These are called rational numbers. Rational numbers are those that can be expressed in the form a over b, where a and b are integers and b must never be 0. Conversely, numbers that cannot be expressed as the above are called irrational numbers. Examples are pi, root 5, root 3, root 2, and so forth. When expressed as decimals, irrational numbers continue without an end. For example, pi is 3.1415, etc., etc., and the same case is root 5. Surds are roots of rational numbers that give irrational numbers. Note that the presence of a square root sign doesn't necessarily mean that the number is a surd. For example, cube root of 8, square root of 49, and cube root of 32 are not surds, because the cube root of 8 is 2, square root of 49 is 7, and fifth root of 32 is 2. Simplification of surds. For surds of the nature root xy or root x over y, we can also have them as root x times root y or root x over root y. These facts are used in simplification of surds. In simplification, the number under the root sign is expressed as a product of two factors. For example, root 50 can be expressed as root 25 times 2, and therefore root 25 is 5. So we shall have 5 root 2. Similarly, root 3 over 9 can be expressed as root 3 over root 9, and we end up with root 3 over 3. Further examples simplify the following. These examples are illustrated below. Conversely, a surd of the form a nth root of b can be expressed as a root of a single compound numbers of the form nth root of a raised to power n b. Thus, 2 root 5 is equal to root 2 squared times root 5, which gives us root 4 times 5, and that is root 20. Further examples are illustrated as follows. We jump over to order of surds. The index of the root of a surd is its order, meaning root 14 is of second order, cube root of 9 is of third order, and fourth root of 64 is a fourth order surd. By expressing the given orders in their lowest common multiple, we can compare surds of different orders. Take an example. Arrange the following in descending order: cube root of 19, root 23, and fourth root of 120. In the solution, the orders are 3, 2, and 4 respectively. The LCM is 12. Therefore, we can have cube root of 19 can be written as 19 raised to a third, which is also equal to 19 raised to 4 over 12. This can be written as 12th root of 19 raised to power 4. And this will end up with 12th root of 130,321. For root 23, it can be written as 23 raised to a half, which is also 23 raised to 6 over 12. Simplified becomes 12th root of 1480,35,889. Finally, fourth root of 120. Following the same ideology, we are going to have 12th root of 172,800. The order is thus: root 23 is greater than fourth root of 120, which is greater than cube root of 19. Like and unlike surds. Surds are alike if they have the same irrational factor. That is, 2 root 3 and 4 root 3 are alike. 2 root 3 and 3 root 2 are unlike. Like surds can be added or subtracted directly. For example, 5 root 3 minus 2 root 3 is equal to 3 root 3. Root 27 and root 12 are alike because root 27 can be expressed as 3 root 3 while root 12 can be expressed as 2 root 3. Multiplication of surds. This is done in just the same way as algebraic expressions. Rational factors and irrational factors are multiplied separately. For example, 2 root 7 times 3 root 5, we shall multiply 2 times 3 and then root 7 times root 5, and we'll end up with 6 root 35. 4 root 2 times 3 root 3 will have 12 root 6. Surds should be simplified before multiplication. For example, should first be written as 3 root 2 times 3 root 2, and then we end up with 9 root 4, which is equal to 9 times 2, giving us 18. Note that for like surds, the product is a rational answer. That is, root 5 times root 5 is equal to root 25, which is equal to 5. 2 root 7 times root 7 is equal to 2 times 1 times root 7 times root 7, giving us 2 root 49, and the answer is 14. Rationalization of surds. We've seen that the product of like surds is rational. This is called rationalization. When a fraction has a surd denominator, It is rationalized by multiplying both the numerator and the denominator by a surd that will make the denominator a rational number. This way we shall have rationalized the denominator. For example, rationalize 1 over root 7, 2 over root 5, 3 over root 3, and 2 over 3 root 5. In our solution, 1 over root 7 is multiplied by root 7 over root 7. Multiplying the numerator and denominator separately, we shall have root 7 over 7. Therefore, we have rationalized the denominator. Take a keen look at the other three examples. Now consider root 2 plus root 3 times root 2 minus root 3. Remember, in the difference of two squares, a plus b times a minus b was given as a squared minus b squared. Thus, if we expand root 2 plus root 3 times root 2 minus root 3, we shall have root 2 squared minus root 3 squared, and we shall have 2 minus 3, and the answer is minus 1. Equally, root 15 plus root 7 times root 15 minus root 7 is given as root 15 squared minus root 7 squared, and the answer is 8. Surds whose product are rational are called pairs of conjugate surds, as above. For example, rationalize the denominators in the following. In our solutions, we simply multiply the denominator and the numerator by the conjugate of the denominator, and hence 3 over root 2 plus root 3 is equal to 3 over root 2 plus root 3 times the conjugate of the denominator is root 2 minus root 3. If we multiply, we will have rationalized the denominator, and we end up with the answer as 3 root 2 minus 3 root 3 over minus 5. The same principle is followed for the next two examples. That brings us to the end of the topic on surds.
I love that math generally has initially clear and precise answers, that you know when you know it and you know when you don't know it. As you get farther on in it, the answers are not so clearly in the back of the book, but initially math has answers, clear answers. Sometimes they're hard to find, but that clarity. The second thing I love about math is it's a puzzle solving kind of, if I can figure it out, and the joy of figuring it out, the kind of sense of accomplishment, the sense of excitement when you get it, the challenge of trying to get it. It's that puzzle solving kind of thing that I really, really like.